is this working? Yes, fantastic. All right, thanks everyone for coming. Let's get started, we have so much time. So, as you heard, we worked in a project called Mongoose IM, which is, in this case, a messaging system, XMPP based. You will see some of these examples in a second. Let me tell you a story about separation of concerns. In the case of XMPP, there is two RFCs. One is the core protocol, and there is a second RFC that talks about presences, which is, you go on a messaging system, your friend is online or not, and list of friends and all the other details. And the protocol XMPP, the X, means extensible. So then there is a million documents with like all the possible extensions, things that you could imagine your messaging system would have. So the core protocol looks something like this on the application layer. You open your TCP connection on the network layer, then you start, the server is waiting for the client to send the stream start. The client says, okay, I'm ready. You discuss some features that you can discuss before authenticating. Usually you go directly to authentication. It's a SSL authentication, which can have a round trip if it's a scram. So then you go for waiting for SSL response, or you are authenticated directly. You restart the stream, discuss a bunch of features, and then you have a connection in which you can already start messaging. So how do you implement this? More or less, a lot of the code that you're going to see will not compile. It doesn't matter. Like it's Erlang readable. It's supposed to be just a guideline. So you implement it as a state machine, like many other protocols. For example, TLS so often is implemented as state machines. So in this case, the same. So you have a state, wait for stream. Then it has like two substates if it is before or after authentication. And you wait for this event, and you have your data. You have the state, wait for features before, and you wait for a specific event. If everything is correct, you go to the next state for features after, and then you have the session established that just goes on a loop, like you send messages, you stay on that state until you decide to close the connection. Now we go with the first extension. So stream resumption. You go from mobile to Wi-Fi, you want to resume the stream. So in your state, you add a feature that you're going to match. So after you have authenticated, you can enable this feature. And now this gives you like, there is a new event that you can match. And over there is a new state that you will also have to write code for. Now you can also have token resumption. For example, like cookies in your web world. So you can jump a lot of things with this new event. You go directly to session established. So in your state, you pattern match a new event. Now you have fast authentication, in which you can use a different kind of token and jump to a different position. So again, you pattern match on a new event and do the logic, and you jump to the state. Now you also have, for example, register. You cannot authenticate because you don't have an account yet. So you have to register, and here you come back to the same place, and you can continue with authentication. So you again pattern match on the new event. And now in this case, for example, after you're sending messages, you have privacy lists. So the processing of the message gets a bit more complicated. And inside of the state, you have certain case logic. This is getting not very happy. Like code is growing in not the way we wanted it. It gets worse. The code gets very wet. This was implemented back in the days as, again, FSM. So, you have synchronous and asynchronous events. Everything is duplicated. And also you have handle info, handle event, handle seek event that people that were around back in the FSM days knows why this wasn't pleasant. And it gets even more complicated because there are two processes. So this is implemented in the application layer. You need to get the TCP packet. Let's say that is encrypted. So in Erlang, you get, again, this doesn't compile. You get this TLS thing that you have to decode. Then you have to decompress it if you have compression. Then you have to parse the binary to the data structure that the protocol uses. It was implemented this way because also back in the days, TLS, for example, or XML were implemented in pure Erlang, and they were very slow operations. So it was nice to separate it into processes. So while this one prepares the whole thing, this one runs the protocol. So a lot of duplication, more and more pattern matching. It's two processes. And this was about separation of concerns. I'll be back.
Well, so actually it's not the first time that we've removed any technical debt. We are talking about the release 6.1 of Mongoose IM. And as you can see on this diagram, like some features are about to be added, and we are reworking the so-called C2S process, which is like the process handling client to server connection, and that's the state machine that we've been talking about. And we need to remove some technical debt. We've done similar things in the past, actually. Like for the couple of releases before that, we've been like removing technical debt and replacing it with new functionality. And the pattern repeats. And I really think that you really need to get rid of some technical debt to add some new features. That's how it works. So let me give you an example of what we did in the past and how we could maybe possibly use it to rework this monster that we've talked about. So for example, one of those reworks was the configuration rework. So back in version 3.7, Mongoose IM configuration was done in a file with Erlang terms. And it was really difficult for non-Erlangers especially to configure. And the config processing was really, really complex and kind of inconsistent. There was like no rule how it works. It was ad hoc code. And the configuration was stored in Nisha and ETS tables. Difficult to maintain. So we also needed to get rid of this part of technical debt. How did we do it? So we decided to implement it side by side so that the new code is implemented here. The new configuration is stored in TOML, and there is a TOML configuration processor. And for each node in the TOML document tree, it runs over 5 steps. And it's pretty well defined. I will not go into details of these steps, but as you can see, it's well organized. There's now a config specification, which is declarative, and it declares like for each node how it would be processed at each of the steps. And the interesting part is here, because we are still outputting the old configuration format, and then that's because we didn't really want to work on this, because this was the old messy code. So we left a whole amount of the old dirty code here. We only had to have a bit of friction here in this a bit complex steps. Why? Because we needed backwards compatibility to support both formats at the same time to give the people time to convert. But then we got rid of that. And that enabled us to finally replace the old format with new internal configuration, which is now stored in persistent terms. That was about the time where actually persistent terms were introduced into Beam. So yeah, and finally we could also get rid of this. So yeah, that's one of the examples of how we in a few steps got rid of technical debt. And I have a second example, second story. It's a story about API and command line interface. So in version 5.1, to configure your API, the REST API, you need to configure a lot of modules, like a lot of different modules in the configuration file. And it gets worse because some of those modules were calling commands registered in the REST command registry, and you also needed to enable some of the commands that actually registered that. So yeah, it was really complex, unnecessarily complex. And well, it gets worse because the part on the right, which is the command line interface, was completely independent from the one on the left, which was REST API. And both used arbitrary, just called arbitrary code in the system, arbitrary low-level calls, and there was no single line of code shared here. And the coverage of functionality was also inconsistent, so that you could have some functionality in REST API, but not in command line interface. It was terrible, and we decided to start the rework by reworking those REST API handler modules, replacing them with fewer ones, but well-defined. We introduced completely new code, which were some kind of new internal API modules, and these are the only entry points to the lower level stuff. So you can only call those modules and nothing else from the API. Well, yeah, now we can remove this. We can remove this. No REST command registry anymore, because actually it was unnecessarily complex. Then let's reorganize things. It's the same thing, but we've made a lot of space, and we fill this space with the new GraphQL API that we've introduced. This is completely new code. Yet again, we are not working on the old messy code, trying to develop the new stuff in parallel. And the GraphQL schema is the central point, and the single source of truth defines all the operations that are used by the command line interface and the GraphQL handlers, and the resolver modules are also using the internal API modules that we've already used. So that's code reuse at work. Yeah, it's much better than before. And then we can get rid of this, and we can get rid of this after some period of backwards compatibility, of course, because you cannot just drop REST API just in one release, right? So yeah, and finally we'll be left with this. So these were like 2 quick stories of technical debt removal in steps. And we just need to take one of those steps, but this time it will be a huge one.
Let's kill this thing. So, state machines. They are models that represent system behavior. By the way, one little trick, if anybody is like into cheating thing, if anybody is into like computational theory and so on, state machine is a less powerful machine than a Turing machine, but these state machines have infinite memory, so really they are all Turing machines, but it's a model. The model represents an easy way to visualize the complex flow through the system. As you saw in the diagram, you have an event, you go to the next state where you accept this set of events, and you go to the next state, and diagrams are readable. And it's nice to have this diagram next to this 8,000 lines of code monster, so you get the idea with the diagram very fast. Let's come back to the diagram. This was the core code before we started adding all the stuff, and more or less the basic implementation. Here I have also, I have a laser. I have also added here the part about processing the packet. So, what are we having here? I was going to say, some time ago, I was working with this client that they had this beautiful idea that I want to introduce the idea to everyone else who is a manager or a Scrum lead or whatever. They had Tech Dev Fridays. That means one Friday in the sprint was 9 days, and one day was find some technical debt that is driving you crazy. That was so useful. So we started thinking, okay, in this case, really what you have is 2 different states. And you distinguish the 2 different states using what to this process is global memory. And something similar you also have here. It's a complex state. Imagine that you want to implement retries. And you have, you can retry 3 times. If you didn't authenticate, kill the connection. Here, you will store the number of retries left also in the global memory, in what we call data. What in a Ken server is called the state, but in the state machine is not the state. In the state machine is a data. The state is the name. So we have complex states here. Another issue that we have is that the events can also be very complex. They trigger like a very complex processing that in this implementation we separated it in stages. So what we need is to represent complex states and complex events. Now we go to all this stuff, and this is just a few examples. There is the second RFC about presences and roster, the list of friends, and there is over almost 500 extensions with different status. Some of them are final, experimental, but there is around 500. So this is just a few examples, and then add your own. So what we have is again, complex transitions that are not part of the initial implementation, and new states. We need to represent complex states, complex events, new transitions, and new states. So let's go step by step. Complex states. This is immediately when I was checking, okay, this is GenFSM, let's do GenStatem because it's what OTP offers. And OTP had this callback. You can configure your state machine to use a single function that is handle event, and then the state doesn't have to be an atom, the name of the function. It can be a data structure. There we have it, complex data, complex states. And now the state is a parameter. So you have the type of the event, which is going to be info, call, cast, internal, etc. The content, which is like the actual content, and the state. And now we have data structures. We have wait for stream before authentication and after authentication. We have the waiting for SASL response or waiting for the authentication that can have some authentication data that it's only relevant to this state of the state machine. You don't need it forever. And the number of retries. Now we have complex events. This is my second favorite thing about GenStatem. You get the TLS packet, you do the cryptic code, whatever step, and ad hoc you generate new events of type internal. And GenStatem assures you that all the events internal that will have the type, as you see in the pattern matching internal, are events that you created in this mechanism. So in this way, the GenStatem offers me a way to introduce this staged processing. Now, the extensibility part. XMPP, the X is extensibility, and we have all these extensions. So how do we do this? I gave a talk last year around this time of the year in Code in America, where there was a little bit of it, where I was talking about hooks and how similar it is to telemetry. Go for that one because we have so little time, but it's something like telemetry. I'm assuming that most of you will have some familiarity with telemetry either on the Erlang or the Elixir side. So in telemetry, it's, if you are from the object-oriented world, I'm sorry for this, it's the PubSub model, you subscribe handlers, there is an event, you trigger all the handlers. But in telemetry, you execute all the handlers in any order. Here we do something a bit more powerful, but also more complicated. We have an event that will have a name key. That's our event. We have an accumulator and the parameters for this event processing. Very similar to telemetry. We check in persistent term the list of handlers for this key, and now we run them as a fold, where the accumulator is given to the next handlers. The handlers have an order, and this is part of our job as the implementer to ensure that the order will be correct. The handlers can add data to this accumulator, check what the previous handler did or not. This is how I'm going to introduce loose coupling between the extensions without touching the core code. If one extension needs another, it just runs in the handler after and checks the accumulator what the previous one did. And the handlers will run okay and just run the next hook, stop, and just stop the whole processing because you know that I don't want to run all the other extensions for whatever reason. Or if there is an exception, just log it, you do your metrics, whatever you need, and continue with the next handlers. And we plug this here. We get a packet, the TLS, the code, etc., etc. We generate the internal events with a type XML element. XMPP is a XML-based protocol, so this is our internal data structure. Given a state, given an event, we know the state, the data. We create the accumulator based on internal data and the content of the event. We check the name of the event that we are going to run based on the state that we are in and the data of this state machine. We run the hook, and we get again OK and stop. If we return OK, then we route the message, we deliver it, everything is fine. If we get a stop, we just don't route it. In both cases, we go to this second step, handle state after packet. Now, the state machine engine that will have just the code that you saw before with these 5 steps with complex data structures and all the event handling, here it will get from the accumulator requests that the extensions gave to this to the state machine engine. For example, they can say, please create another internal event processing, and then like process this new event that one of the extensions created. Or state machine, please jump to this different state that the extension is creating. So now I have one module. The previous module, the previous C2S code was around 5,000 lines of code, plus the GenFSM that was copy-pasted because OTP removed it, plus the receiver process that was already around 10,000 lines of code. The new module is 1,000. And then move all the code to the extensions, of course, because the old code had code hard-coded into the core module. So, and in this way, hasta la vista, baby.
Okay, now it's my turn again. So, yeah, I like summaries in tables, so I will show a few. So the first one highlight is that now the new implementation, which is called Mongoose C2S, it implements only one RFC, and I think it's really important because here you can see like how many of those extensions that or bits of functionality from different extensions were just hard-coded into the previous state machine. So it was really a mess. And they are described in separate documents, as you can see, separate from the core RFC. So they should be only used and only enabled when you enable a specific module in the configuration file. That's the idea. It's very modular. You can enable any set of extensions that you want. And it's really good that we've extracted bits of functionality out of this huge God module to the places where they should be, to the extension modules. And this is all possible because of this loose coupling with hooks. Okay, next one, the hooks. This is a list of the list of hooks that are related to this client to server state machine. So as you can see, the hooks are mostly triggered by XMPP traffic. So user session opening, closing, and the messages, right? In XMPP, messages are XML elements, so this is why you have hooks for incoming and outgoing XML elements, which are called XMPP stanzas in XMPP, but yeah, that's just naming. And there are a few types of those stanzas, that's why you have a list of hooks instead of one. The last row is a bit different. I will try to describe it shortly. It's a bit more difficult to understand maybe, but yeah, it's a hook that's called on demand. It's when you want something from another process that is handling another user. I will describe it in a moment. And of course, the hooks would do exactly nothing without handlers. So modules, extension modules have handlers, right? As Nelson has already said. So each handler does its own logic and then returns accumulator, and then the accumulator can tell the C2S process to perform some operations after handling the hooks. So one of them would be to store some module-specific data in the C2S process, or to transition to a new state, to perform some actions. These are gen-statem actions, and stop the state machine or deliver some XML elements to the user. And now an example. What is mod presence? Presence is just users being offline, online, and how one user can be subscribed to some other user's presence and see if they are online or offline, for example. It's more complex, but yeah, it's in a nutshell. And the triggers for the first two hooks are just when you send or receive presence elements, and then the handler just instructs the C2S process or the client-server process, the state machine, to put some presence information on in its data. Okay, that's quite simple, but what's this thing? This is more complex. So this is where one process that's handling one user wants to, for example, get the presence information of another user. Then you use Mongoose C2S call, which in turn uses just gen-statem call, and yeah, and that handler logic gets the presence information. Okay, this all happens in mod presence, but the last example I think is most interesting, because mod roster is yet another module that implements so-called roster. Roster is just a list of contacts. So where you change the contact lists when you have a new contact item, for example, then you want to change the presence subscriptions. This is in mod roster, this is in mod presence. So this is how we loosely couple the modules. So mod roster calls this, and mod presence is just subscribed to a hook. So it has a handler. So, yeah, so this is loose coupling between modules. And before that, it was just a piece of mod roster that was like hard coded into mod presence, which was not the best way. And finally, I would like to outline a few of the highlights of GenStatem that we've used and that made it all possible. So it's funny because I'm talking about this as being like new features, but I know that they have been introduced since OTP 19 and some of them in 22, I think. But yeah, old stuff is like, I think is like when it was like R7B or something. That's old. Okay, so the first thing is that we are using the state event function. So there is like a handle event function, right? And we have these complex states that are tuples. That's the first feature that we used. Another one was that modules can have external states. So for example, mod stream management, this is an extension that makes it possible to resume a session. So it has a special new state. So an extension module introduces a new state to the state machine, which is called external resume, and the old session enters that state just to wait for a new session to be created, and then the new sessions can use some of the data from the old session. That's the idea. So when we introduce a new state, we need a new function to handle that state, right? So this is why we need to use the push callback module action of GenStatem to temporarily change the module that is handling that state machine. And temporarily, like mod stream management takes control, and it has its own handle event function that's handling that special state. We are also using various types of timeouts. Two examples. The first one, for all states before the session is fully established, if like the client does nothing anymore, we just terminate the session after timeout. That makes sense. And the second example is about named timeouts. I know they are also called generic timeouts, and these don't expire with state transitions. These are like, for example, mod ping is a module that enables the server and client to ping each other on an XMPP level. So when there's a ping, you wait, of course, for a response, and the timeout is a perfect tool for that job. And finally, for example, self-generated events. So that means that when there is raw data on a socket, whenever we parse it to an XML element, we just generate a next event. That is that XML element that will be handled next by the state machine. And I think that's it.
That's pretty much all. So this work, as I said, it was introduced on this, again, for managers, Tech Dev Fridays. It was very useful. We prepared a prototype with the basic core, a couple of extensions. Looks promising. Okay, team, let's do this. It was released last year. Was it 6.1? 6.1, right?
6.0?
Or 6.0?
I think 6.0.
6.0, maybe. And as a side note, just a curiosity, when I put this on this client that I was working on, it also had like a lot better performance. For once, that was not my intention. For those of you that know me, you know that I'm obsessed with performance, and I usually like everything I do has to be faster. For once, this time, I wanted the code to look beautiful. That's all. I was like, I'm not going to, like, it's just beautiful. And it was faster, so it was cool. Anyway, with that, the monster is dead, and we have a new implementation that is extensible. Hopefully, you learn some idea for how to implement a similar case. Thanks. That's us.
All right. Thanks very much. I guess I was right that if you make it beautiful, then usually it gets faster, right? Right. Any questions? Yeah.
As far as I remember, the old P1 FSM, all that behavior that was used for the CTOS process Wasn't actually just a copy of the FSM from OTP. It introduced, for example, a very poorly working mechanism of controlling the incoming message queue. Well, it was based on self-inspection, so when when the process was stuck, it wouldn't work anyway. But I was interested whether you try to replicate, at least to some degree, this behavior, or just try to implement it in some different way.
Yeah, so the idea of that one, because it was a copy of GenFSM with then some changes, I believe that back in the days, but again, this was a very old time ago, that was done because of like the way the implementation, the processes were receiving the messages, and you can just queue them in the process memory. Like, I didn't try to replicate that whatsoever. GenStatem has a very similar mechanism. There is another thing that you can do with events that we didn't use in this case, but GenStatem offers you, that you can postpone an event. And there is another one of those actions like timeouts and internal and so on, and push callback mechanism. There is another one that you can like check the documentation for the specifics. You can say, please process this event after the next state transition or after the next event, and just keep it postponed. Either in this state, but when something else arrives, or just postpone it until we transition to a separate state. GenStatem has something similar.
And the second question, so when you mentioned that in certain situations the callback module is changed and you said it's temporary, but you mean that the new callback module has to give up the control explicitly, right? It's not like controlled by the original callback.
Yes. Yeah, but it's on the extension, so there is the same way that you can add this action push callback module, you can also say pop callback module. Anybody can call it. That's where we need to be responsible and not introduce a spaghetti. It's usually itself when a new event arrives.
Okay, thanks.
Yes.
So, thanks for a great talk. I have a remark I would like to add, not really a question, but we could read between the lines in your presentation that there are some features of XMPP that are sometimes criticized for example, that XMPP is chatty because you have to extend all these presence probes, all the presence information, so there is a lot of overhead in the system. But for our use case, we don't really need presence. And here we can clearly see that it's not a matter of XMPP, the specification, it's rather a function of how it's implemented. With proper implementation, with loose coupling, we can just disable presence if we don't need it in our product. And that reduces the performance overhead.
Yeah.
So
and the memory overhead.
Yeah, the memory overhead.
Yes.
And
forgot to
that's
mention
it.
that.
Yeah, and we've load tested it, and it indeed is faster without presences.
Yes. So that's another thing about this loose coupling, that now you can disable those things. They were hard-coded into the core code. Like, in a way, it's how it grows. Like, it's easier to implement this now. Like, now, after 20-something years of XMPP, I know, like, the core and an example, like 470 examples of extensions that you can do. So it's easier to implement this extensible now. But it's how the code grew back in the days, when there were like 3 extensions and, 20 years. You can disable them. That's a great performance optimization.
And actually, like, the standards also evolve.
Yes.
Like, the former RFCs were, let's say, worse than
Yeah, yes.
yeah, and so we took some inspiration, of course, also from the revised RFCs, and that they explicitly specify that some things are now optional that weren't before, and that, for example, you could now optimize the way the SASL works, or the whole like connection setup and authentication, everything. And we've already like implemented some of the extensions to make it all less chatty, let's say, and verbose.
That was also one of the reasons why we wanted to kill this, because this was implemented with a previous RFC 3000, don't remember, but there is the 6120,
I think,
has a few very important changes, but it was just impossible to like touch the previous code, and like it just grew into this spaghetti. So it was a way to, okay, just I'm going to implement 6120. Like, I'm not going to look at the whole thing. That's it, just 6120, and it was a good chance also to upgrade.
So from the XMPP implementer's perspective, it was kind of common knowledge that if you want to cut out some of the parts of the protocol, like you knew what to change in, for example, in the code base, but you had to have a fork of the server, disable some parts, and then you had an XMPP system without presence. Now it's just a matter of configuration.
Another question? No? Okay. Thank you very much, everybody. Give a warm welcome.